So my name's Craig, and this is a talk about hunting cloud exfiltration. And my background is, I won't go into a lengthy background, but my background is I've worked on a few security products, that some of which you might have used, mostly in the SIM or security information event management space. And I've worked on a few private projects as well. I spent a lot of my career working on threat hunting and detection, and in general, and in particular, studying things that were undetected, that went undetected, and finding out why and what to do about it. This usual disclaimer. So what I'd like to share with you here today is I have some case studies that we can look at together and in kind of in an interactive way, so we can do a little bit of threat hunting and analysis together to make it more interesting and more interactive. I'll run through a quick intro to the log types that I'm talking about here, just for anyone that's not familiar with them, just to give you a general idea. I'm going to run through three or four different models of cloud threat hunting using either conventional detection or anomaly detection or combinations of both. Towards the end, I have a case study. I have a live case study of an exfil detection that we can look at and decision together. And then finally, the takeaways. So this is the best problem statement that I think I've seen in this space so far. And this is better than anything that I've come up with. So as I said, this is better than anything that I've come up with in terms of succinctly describing the problem statement, which is that if you read the retros on the major exfil cases that are out there in the public domain, and there are maybe a half dozen or so really big ones, and then there's another few dozen smaller ones that are out there you can read about in great detail. But this is essentially the reason that they weren't detected in real time or something approaching real time or early enough to disrupt and make a difference, is that most of the time we're talking about credentialed access. We're not talking about exploitation, execution, and persistent cycles. In some cases, of course, there are. But in many of the bigger cases, we're talking about credentialed access where a legitimate user account's been compromised and somebody's coming in that way. And the difference between the ordinary user activity, which is benign, and the activity by the threat actor that's hijacked the credentials, the difference is subtle enough. Sometimes it's a matter of nuance, and sometimes it can be hard to see. So in terms of indicators and things to kind of hone in on, in the big 4 or 5 case studies out there, most of the time we're talking about S3, or the simple storage service, which is essentially a nearly unlimited object store in terms of capacity. It's very vast capacity, high performance, where you can put files into containers that are called buckets. And in bucket, you can think of as, it's almost like a file folder. And you can nest buckets like file folders like you would in a file system. And you can call these from anywhere in the world using an API. And this is it's performant, it's inexpensive, and so it's become very ubiquitous in that the S3 service is used as the data layer for an increasing number of applications and systems and things. And so there tends to be a lot of people tend to go after S3 because there just tends to be a lot of data in there. In one of the first cases, and the second line is an event called modify snapshot attribute. And what a snapshot means, if you're not familiar, is in the cloud, a snapshot is actually quite similar to what you would get from, say, a VMware snapshot if you're running VMware at your desk. It's essentially just a point-in-time disk image of a virtual machine. And so this was an earlier case. This was one of the first. But what happened is, rather than using conventional means, this was something we hadn't really seen before at the time, and I'm not sure we thought about, but what happened is a threat actor was able to compromise a user account, and they were able to share snapshots with their own account. And the reason you can do that is because snapshot sharing in itself is not suspicious or malicious in any way. Snapshot sharing is used sometimes to share images and data between different accounts, because many teams, it's often the case that teams will each have their own account for reasons of sandboxing, so that a mistake by one team cannot affect another team and vice versa. So there tend to be lots of different accounts in many environments. Another reason is that there are an increasing number of security tools that will do so-called agentless security detection, and scanning, and malware detection. And the way they do that is rather than running an agent on a virtual machine, they'll actually take a snapshot and they'll scan the snapshot for evidence of indicators of malware. So there was a time when that event was relatively low volume enough potentially to examine or scrutinize. But given the rise of tooling that uses snapshots and other things today, the volume can be quite high. And what I mean by, and finally, get caller identity is, it's more or less like the who am I in this API, in this cloud API. It's basically like, what is my user context? And that's useful because sometimes it's a precursor. In some cases where it can be a precursor event to privilege elevation or lateral movement or possibly other things. But the normal prevalence is, the normal prevalence is the numbers that I've observed of these in all of the production CloudTrail log sets that I've worked with at scale. These are the ranges, the prevalence that I've seen. The list bucket event, so the list bucket event it's very, it's voluminous because the first step in grabbing files from a bucket is you call list buckets in order to enumerate bucket names, and then you can start to enumerate file names and then get the files that you're interested in. So this command, in some place that, in a smaller environment, you might have, say, 10,000 instances of the list bucket command over the course of a month. In a larger environment that's using S3 as a data layer, you could have more than 100,000 of these per month. And modify snapshot attribute can vary. It can be all over the place. It can be relatively small numbers or it can be very large numbers, depending on how much snapshots are being used. So these numbers are too large for conventional alerting, right? We can't really think about alerting on these events by name because the volume, the frequency is just too high. In terms of numbers, the numbers that I'm citing for the makeup and the vectors in these exfiltration cases are coming from this repo. And this is a repo where a researcher gathered and published a lot of data about what's known about some public record incidents. And most of in the customer reported incidents, if you break them down by tactic, the overwhelming majority of them fall into the category of credentialed access. And that's not to say that there are some kind of traditional exploitation, execution, persistence cycles on virtual machines as well. But in the customer reported incidents, credentialed access is much more prevalent, either because it's easier to execute or it's simpler to operationalize for threat actors or for whatever reason. So in terms of the data that we're going to be working with today, who's worked with CloudTrail logs before? So, okay, good. So about a third. So in order to talk about this today, we don't need to know everything about them. We don't need to know a ton about them. But in general, the format is, and these are simplified events, but what you've got is a source IP address, an event source, and each one of these is a single API transaction. And the API method is called an action. And the action is in the event name. So you've got a source IP address, where it came from. The event source is the name of the service that the action was transacted in. The event name is the name of the action that was called, which is essentially an API method. And then the user identity is what it sounds like. It's the unique user identity who made the call. And these are just 4 fields. These are some of the 4 fields we'll be working with today. There are a number of more, obviously there are many more fields in there. There are request parameters and response parameters. There's account information. There are a number of other fields. But these are the major ones that I'm going to be kind of honing in on for anomaly detection today. Something else to know is that these can be enriched with things like geographic information and autonomous system information. Autonomous system, what I mean is using, these are generally not enriched by default with this data, but using a third-party database, like there's a popular geo database that's published by MaxMind, and there are probably others, but Using a third-party database like that, you can enrich these with things like the source geography associated with the IP address, like city, province, country. You can even get latitude and longitude if you want to plot them on a map. And then you can also plot them with the AS name the AS name and number is the name and number associated with the network where the IP address lives, in terms of who was the internet service provider for that IP address. And the reason those are useful is, so this is what a curve looks like for, if we count source IP address, counting unique source IP addresses in CloudTrail data at great scale, it kind of looks like this, and that there's a small number of IP addresses that generate huge numbers of events, but then there's this long tail of IP addresses that generate a few events. And there are enough IP addresses in the tail, the volume is high, but also the variability is high, in that because these cloud services are so distributed and they use IP spaces that are so vast, that these IP addresses can, even for a single instance, a virtual machine instance, if you power it off today and you power it back on next week, odds are it'll get a new public IP address that it had before. And sometimes that could even happen, day to day or even intraday sometimes. So there's a long tail of unique IP addresses that is changing more or less on an ongoing basis. So it's pretty hard to do. It's hard to use source IP as a good indicator or a good primary key for doing anomaly detection or doing threat hunting in general. With a few exceptions, there are a few ways to do this by grouping IPs, but individual IPs it gets harder. But if we enrich these with geo information and ASN information, then the picture gets a lot simpler. In that this is a count of, so in this same data set, there were 29 unique source networks, and most of the activity is coming from the top 4, and then there are a few outliers, and the outliers are things like, so the top 4 is going to be production traffic coming from busy workloads and machines and accounts. The outliers tend to be things like developers, dev test folks, SREs logging in to fix things. Because with people in the post-COVID era, with people working from home, people are all over the place. And people roam around, but sometimes even between countries. One thing that works well in terms of ASNs is that people roam around quite a bit, but they don't always change networks that often. Like in my case, I have a cellular network provider, and I have the same provider for both cellular and internet access at home. And that's about it for me. And the only time I change networks is if I'm in a hotel or someplace. But there's some geography that I can associate with that. So in terms of search space reduction, if you're thinking about getting in here and doing some data sifting and analysis, one thing you can do in order to shrink the search space here, make it a lot smaller, is assuming we have autonomous system network names, we can then separate, and we can ask questions like, how much of this is coming from my cloud provider, my cloud environment, and how much of it is not? How much of it is coming from the outside world based on network names? Because there'll be a short list of ASN names associated with the cloud provider, and you can simply exclude those. And if we exclude those, and then focus on, say, just a production account to start with, because dev test accounts, they tend to have a lot more variability and a lot more variance. Production tends to be more predictable in that it tends to behave similarly over time, and not always. There are always new behaviors as automation changes, infrastructure as code, but it's less unpredictable than, say, it's less unpredictable than dev test, but also the product count is probably where the data lives that we're most concerned about. Not necessarily, but probably. So if we do that, now we've got most of this activity is coming from 2 ASNs, and that's production workload. And then there's a small tail of a half dozen or so other ASNs. And those are either low volume services, or those could be SREs or developers that are working in prod for some reason, either because they're fixing something or they're deploying new code. And if there are, then there's probably, depending on what the process is like, if there is an SRE or a dev working in prod, there's probably an open ticket associated with that you can use to reason about, to decide about whether or not it's expected behavior. So in terms of what we can alert on, so we'll start small, we'll start simple, and work our way up to more complicated things. And the reason for the mixes is I'm not here to say just use anomaly detection and nothing else, or machine learning and nothing else, or AI. I'm not here to say use technology X for everything everywhere and forget about everything else, because I don't think that that's how we succeed. I think we get better results by combining technologies in complementary ways. And in some cases, like if there is something that we can detect with a search that takes us 5 minutes to write, and it takes there's almost no cost in execution in running the search, then it's preferable, we have a better resource to kill ratio and just running a conventional alert rule on that than we would in using a machine learning model in terms of cost. So these are, of all the potential exfiltration related events that I've studied, this list is sparse enough, it's infrequent enough that it's feasible to alert on these. Or not necessarily to alert on these, because they wouldn't necessarily rise to the level of something that you want to get into an alert queue and have somebody jump on and investigate immediately. But these could be fed into either a threat hunting queue or an alert queue with maybe a medium or low severity. Because in the data set that I've studied, these will generate, the numbers here will be single digits per week at most, and sometimes single digits per month. So a very small trickle of these, so not enough to become unmanageable. All right, so we can, and in terms of what this would look like, I put this in Sigma format because it's a nice kind of vendor neutral format. So this is not a complete Sigma rule, but this is because I wouldn't fit on screen, but this is what the section, if we put this into a Sigma rule, this is what the detection logic, the core logic section would look like for these. This is another one. So another good potential hunt is north-south S3 activity. And what I mean by that is S3 data activity that originated from outside your VPC, from outside your cloud account, from somewhere outside in the world. And because remember, we had in the prod table, most of it was coming from a couple of ASNs, and that is almost certainly going to be benign because it's high volume and it's working in prod, and it's going to be activity that we can most likely reconcile as benign. Where you have, so in this case, what we're doing is we're excluding anything coming from a cloud provider network using these 4 ASN names, and then further excluding anything coming from a private IP address, because if the event is coming from a private IP address, it means and we're able to see that, it means it's coming from inside a VPC in a private network somewhere. So it's coming from inside the house. And that doesn't mean it's guaranteed to be benign, but it's probably benign. But if it's not, we'll need a different hunt for that I'll get to later. So if you do this, the odds are in prod, there's not a ton of normal S3 activity coming from outside the cloud environment, from out in the world. There'll be some that's quantifiable and explicable, but there won't be a ton. And where we have sources of S3 activity from out on the internet that are extremely sparse and extremely rare, or that are new and have never been seen before. Sometimes those are good places to start a hunt, because in general, with services like S3, most applications that use services like S3, they either use them, they either generate a large number of events, they use the service all day long and generate a huge number of events, or not at all. It's relatively uncommon for a normal service or user to generate a very small number of events, unless maybe they're testing or troubleshooting something. So there's some of the other high volume events here. Some of these actually have alert rules in some projects out there, like assume role and get caller identity. But these, again, so assume role is one of the highest volume events out there, and I've seen it at the high end, I've seen it as high as 84 million per month. Because assume role is essentially, if you're not familiar, it's the way that a virtual machine instance obtains credentials and access, and access tokens in order to be able to do work. So you can define policies and say that this virtual machine is authorized to work in these services. And so the virtual machine can do an assume role and can obtain temporary credentials to work in those services. And so that goes on all day long. And so if you have a large fleet, you can have a large number of those events. And similar with these others, the numbers are simply too large in these cases for simple alerting. So in terms of why anomaly detection, I would say part of the reason is that this is actually a screenshot of a snippet of the attack matrix that contains a technique called snapshot modification that was added here after that snapshot incident. So there's actually a tactic and technique for the snapshot modification exfiltration vector. And you notice it says monitor for anomalous file transfer activity between accounts, which is more or less what we have to do. So in terms of anomaly detection, one of the ways in looking for things like S3 activity, when something wakes up and starts doing massive data transfer or large amounts of discovery for that matter, or a number of other things, if an account is hijacked and it starts doing discovery or it just starts doing bulk data transfer that it hasn't done before, that will usually be visible in a time series histogram like that. Like these are spikes and lows in, this is basically a plot of event name by time, and this is a plot of errors by time. And a spike in errors is often useful because a spike in errors doesn't really have a benign explanation. It may not be malicious and it may not be a threat actor or an intrusion set, but a spike in errors means that something's wrong. A rare error, sometimes I've found it's interesting, a rare error, a new error, sometimes can predict that a service is about to fail within the next 5 minutes or so, and I've had some teams use it that way. But the trouble with this is, I could absolutely, if there is, say, S3 exfiltration going on with some quantity to it, I can definitely see it here within the first few minutes. Definitely within the first hour, and probably within the first few minutes, depending on the time slices that we're using. But the problem is, even though I can do that, the business value is not that great, because by the time I can see it here, if it's been going on for 5 minutes, you can move quite a lot of data in 5 minutes. So if it takes 5 minutes to detect, and it takes maybe 20 minutes to respond, and it's been half an hour, then we could already be well into some significant exfil. And so the business users will say, it's great that you detected it, but why couldn't we do something about it? Like, why couldn't we have stopped this? And that's the hard part, is how do we get early enough in order to try to disrupt this in a way that actually makes a meaningful difference, or a large difference. So we'll talk about simple anomaly detection first. And this is a simple matrix of anomaly functions and combinations of fields. Like human user context is the user field the user identity field we saw. Service name action is basically the API name that we saw in the logs. Source geography is geo. Source ASN is the network name, and then user context is also the username as we saw. And what I mean by the difference between concurrency, new, and rare, and these are things, by the way, even if you don't have, the reason I'm including this is, even if maybe you don't necessarily have a data science team or a machine learning capability, or maybe you're in the early stages or you don't have one up and running yet, these kinds of anomaly detections it's possible that you may be able to do these kinds of anomaly detections in the SIM tool that you're already using in their search languages, if you dig into it. And many of the SIM tools out there, it's possible to do these kinds of things. And so what I mean by concurrency is, that's an older technique, and it essentially means we have the same user coming from 2 different points in the world that are probably, it's not feasible for them to be roaming between them. It's a good hunt, but it has to be checked out because, again, in the post-COVID world, people roam around so much, and sometimes people use ISPs that make it look like they're coming from somewhere else. Business travelers in Europe can roam through 3 countries in a day in Europe. You can roam between the US and Canada in a day. One thing you can do, though, if you have, say you have EDR agents from your endpoint fleet, you probably have IP and maybe even location information from the user's endpoint. So if the user's on a company-issued endpoint, and you may be able to ascertain whether they really are where it looks like they're coming from and whether that makes sense. So that's one good technique. And when it comes to new and rare, and the reason for the combinations is I wouldn't say, it's not always useful to say, just show me the rare or least frequently occurring events by name, or users by name, or things by the least frequently occurring things, because there are going to be benign normal outliers in any when you're looking at any single field. There are always going to be some benign normal outliers to sort through. But if you do it in combinations, say like a service activity and particular action activity for, say, a user context or a source network, those tend to have, they tend not to change as often, and they tend to have a shorter tail of benign normal outliers. So in some cases, in some of the, like for example, in some of the exfil cases we've seen, threat actor, it's often that you'll see a threat actor coming in from a VPN service. And that would mean they'd be coming in from a source network that you've probably never seen before in your CloudTrail logs. In one case, they were using Tor, and Tor. If you have activity coming in from Tor, that's worth investigating in itself, because there's not a ton of legitimate use cases for Tor, at least in accessing production accounts. So in those cases, there would have been a rare source network for the user, possibly for the actions in the service as well, and possibly new or rare source geography as well, depending on, especially if where Tor is involved. If they're coming in from Tor, the source geography is going to be chosen at random. So it's quite likely you have some source geo in there that has not been seen before. This is a simple anomaly detection dashboard implemented in a SIM tool. And again, this is specific to one tool, but it's possible to do things like this. It may well be possible to do things like this in the SIM tools that you already have, or the data tools that you already have, so it's worth investigating. This is using an operator called unusual significant terms in order to find unusual combinations of, in this case, of the user context and the action or the event name. And in this case, there are two sets of 3 list bucket events that are extremely unusual. They're extremely rare. They're outliers in the data set. And so if we could detect those early enough and then potentially do something about it, if we could detect those early enough and make a decision to disrupt that access, we'd be getting closer to disrupting some of this exfil. So one of the things the next thing I want to share is I've been experimenting with deduplication because, because one of the things I found is that there tends to be a lot of cost, conversation, and friction about things like CloudTrail and VPC data. And not because there's anything inherently wrong with the data, it's just because when you have busy cloud environments full of services and things, then the log volume tends to get really large really quickly. And so the cost of ingesting and storing and analyzing that tends to start large, and it gets larger over time. Like in my case, when I was a user, the last time I was a user, I spent north of 1.2 million a year on log ingest, and only a portion of that was CloudTrail. But there was a significant volume to CloudTrail and flow logs. But one of the things I noticed yesterday, one of the keynoters was talking about that data has become so large and so heavy and so expensive that we're going to have to, rather than trying to bring the data and forklift the data to the analytics tools, we have to bring the analytics to the data. And so one way I thought about doing that is, if you look at CloudTrail events, there's a lot of duplication. There are a lot of events that have, in other words, that have identical values in the fields. And those can be deduplicated. And what I mean is, taking the fields that repeat and deduplicating or compressing those. In this case, this is what it looks like. So what this is doing is taking a set of 25,000 CloudTrail events and then running them through a deduplication library that exists in a Python library called Pandas. And what I found is that I can take 25,000 CloudTrail events and I can reduce them to about 400 uniques using fields that tend to repeat. And then I can further reduce that. And so these events have MITRE tactics because they don't generally have those by default, but I added those by hand, so they have MITRE tactics. And so what I did then is in order to do another search space reduction, I removed events with the discovery tag, which is discovery is basically like scanning and enumeration, because there's a lot of those, but there also are better ways to look for anomalous discovery. If I do that, it gets us down to 100 and something odd unique CloudTrail events, which is completely feasible as an input to a threat hunting workflow. 100 or so unique events is not too many for a threat hunter to look over. And the advantage of doing this is that this could be done locally where the data lives. So the data doesn't have to be shipped out to another tool somewhere, which means egress cost for the data, and it means doubling the storage cost because it all has to be copied and stored somewhere else, and it means compute and analysis and license costs, and there's a whole series of costs that could be reduced here, I estimate, by in a significant portion. I plan on adapting that to expanding that to flow logs in the future. So let's talk about anomaly detection first. So what I've done here is I probably can't demo production notebooks here, but even if I could, there would be so many redactions that it wouldn't be as interesting for us to look at. So what I did is over the past few weeks, working with 2 other researchers, I created a set of notebooks that are quite similar. And I created a sanitized CloudTrail data set with 25,000 CloudTrail events. And I put the whole thing in a repo that's publicly available. So even though we won't have time to actually run each one of these today, we can step through them quickly. But then you can take all this home and play with it to your heart's content and potentially use it if you want to. So this first one is doing an ensemble approach and using a package called PYOD. And the advantage of this is that what it does is it takes the 25,000 CloudTrail events and it runs them through a list of anomaly detection models, the popular models that are supported. And then it gives us the output. And the advantage of doing that is rather than running, say, one model at a time and then manually comparing results, it's kind of nice to be able to just run many models at once and then compare all of them, not only see the output from each, but also compare the results that came from each model. So what you'll see is as it runs through, as it steps through the notebook, so those are the output rows that were tagged. That's a heat map. And this is a correlation table. So it does a Pearson correlation between the models in order to see which combinations of models had good output in terms of which combination of models found anomalies. And one of the next things we need to do is to completely process that output. But there are a couple in the 90s. And then what I've done is, you can see here, these are the CloudTrail rows that were tagged as anomalies. You can see there's a lot of discovery and defense evasion. So what I did is I filtered out discovery events to reduce the search space. And then that gets us down to a smaller set that's a little bit easier to read. Then I reduced it again just to exfiltration events. And you can see that we've got our list bucket events here. Anybody see something else? This notebook actually did a good job at finding one of the targets it's kind of hard to find because it only exists once. So down at the bottom, you can see there's a modify snapshot attribute event that's an outlier in this data set. So that one's pretty good at finding anomalies. This next one is running a model called k-means. And what this does is, as k-means, depending on who you talk to, you might hear opinions like if you go and you take there are several classes out there in machine learning you can take at the conferences, and different instructors have different opinions on k-means. Some people love it, and some people don't use it as much. But it's kind of a workhorse anomaly detection model that's used a lot. What it does is it takes our fields and converts them to numbers, and converts them to numbers in a small enough range that they can be plotted in 2 dimensions using a process called principal component analysis. And then it takes those plots, it takes those numbers and it plots, and it creates what are called clusters with centroids. The centroid is the heart of the cluster. It's the central point of the cluster that all of the other points cluster around. And the idea being that when all is said and done, and this is the output, in the final output here, we have similar results to the first notebook. I did a similar thing where I got rid of some of the discovery events to reduce the search space. But the idea being is what happens here is that when it's done plotting the clusters, the idea is that in general, that the outliers will tend to be visible because they'll kind of be far away from the clusters. Maybe not even in a cluster at all, but maybe some kind of far away from them on a graph. So it's a way of finding outliers. All right, so case study. So here's an example of an exfil, here's an example of a potential exfil anomalous S3 access event that was found by one of these. So I had to blur most of this, so I apologize. I know it's hard to read. But there are only really 2, the only important, the portions that we need to see are only the 2 that are highlighted. So the first one up top is, anybody recognize what that is? So the first one is just a URL to an S3 object. It's basically just a request that says, I want this file in this S3 bucket, by bucket name and path and file name. And the second one, starting with XAMZ credential, anybody recognize what that is? So that is, when you see a token starting with ASIA, that means it's a temporary security token. It was generated by the security token service, and it has I think by default it lives for 60 minutes and then expires, although that can be changed. The lifespan can be increased if you choose to. And so what we've got is, this is a little odd because ordinarily, activity using STS tokens, ordinarily that would come from inside your cloud environment, right? Because how did somebody out in the other side of the world how did they even get to your cloud environment to call the metadata service and obtain a token that's valid in your account, right? Because you'd have to be you generally would have to have persistence on a running instance in the target cloud account in order to call that metadata service and obtain credentials like that, right? So how did somebody even get that? So this is just a good example of, once in a while, you get a case like this, it takes a little bit of investigation. So everybody with me so far? So we've got authenticated file activity into the S3 file service coming from somewhere out in the world that cannot be explained because there's nobody there that should be there. And it's using a temporary STS token that I can't explain how somebody outside the company, outside the environment got this token. So who says it's malicious? Show of hands. Who says it's, all right, malicious may be too strong a word. Who thinks it's suspicious? So good, about half. Who thinks it's benign? So nobody. So, and the thing is, both answers are correct because it turns out this actually was an application, believe it or not. And it tells you gives you an idea of just how much S3 activity can be out there. So what happened is there was an application running in a browser that was using an NPM module to make S3 requests. And I think it was an older module, so it was using this authentication technique. So what would happen is when a user working the application said, clicked on the screen and said, I want this file, then a worker node would go and would make a request to a backend service and say, hey, go get this file from this place and take the file and put it in an S3 bucket and generate an STS token. And then the application worker, once that was done, would take that information and bring it back to the user and say, okay, you may request this file at this location and use this STS token. And this is something that was done. This isn't done so much anymore, but there was a time when I think this was done more often. one thing you can do here, if you have activity like this, because this kind of, this temporary security token activity coming from outside your account in places that you can't explain, it's usually a very good hunt. But one way you can get rid of a noise like this is, rather than doing it this way, this could be replaced with using what are called pre-shared URLs. So you can, when a browser or an external application needs an S3 file, you can create and give it a pre-shared URL, and use that URL to grab that file, and then it will expire. And then you don't have any token usage like this to think about, so that's good. In terms of if you wanted to hunt for this, it's pretty straightforward. It's north, so this is north-south activity, meaning S3 activity coming from outside the account, but this time using STS tokens. And so we'd be looking for a similar criteria where it's not coming from the cloud provider, and it's not coming from a private IP, and the access key starts with the string ASIA. And this is a good hunt because if you find something, like you might find some legacy applications out there that are doing this, that are benign, but that's also some good risk reduction. If you do have applications out there that are handling credentials like this, moving to pre-shared URLs is also it's a good risk reduction and attack surface reduction. So, in terms of how do we get to left of boom? How do we do this early enough to make a difference? So we can definitely find outliers in cloud data, in cloud API data. We can definitely find unusual activity. So when a compromised account that doesn't normally use, say, S3, wakes up and starts using it, we could find that pretty quickly using these techniques. And the question is, what do we do? Like, what's next, right? Because I myself would be very reluctant to aggressively shut down a busy S3 process, even if it's new and rare and anomalous. I would be reluctant to interfere in that without at least corroboration or without agreement or concurrency from maybe an application owner, an SRE, or a DevOps lead, or somebody who's familiar with the system and can say, like, yes, that looks like it's normal. Because usually you get one of two reactions: either, oh, yes, it's supposed to do that, it does that, or I don't know, it shouldn't do that. I don't know why it's doing that. And so, but it takes time to get to that. It takes time and minutes to get to that kind of consultation and determination. So, one thing I thought about is, in an organization, say if you decide you want to err on the side of risk and intercede in order to try to reduce the risk of S3 exfil, one thing we could do is not just aggressively shut this down or disable access when we have something like this, but implement a kind of a re-authentication process. And by that I mean, send a push notification, assuming, say, if you have SREs or support teams that are always on duty, if you have teams that are always on, somebody's always on pager duty, you can send a push notification to those teams and say, look, can you re-authenticate this, that this is normal, and get a yes, no back. And if the answer is no, then, and if the answer is no, it's probably not normal, it's probably suspicious, then turn it into an incident, and then maybe start to take more aggressive steps. The only trouble with that is, in order to make a difference, though, because all of this is going to take time. It's going to take time to generate the case, to get the push out, to get somebody to look at it, make a decision. And while time is going by, if this is exfil, data is going out at a good pace. So that isn't necessarily fast enough. The only way to make it fast enough would be to get more aggressive and shut things down that trip anomaly detections. But that's not going to be a cultural fit for many organizations, because the risk of business disruption there, I think, sometimes can be a little bit more than we want. So I think what we need to, in terms of thinking about this, one thing we can do that potentially could have a lot of a benefit but not much impact or cost is start trying to get thinking about prediction. And by that I mean, the more we can identify accounts that were involved in exfiltration cases and their attributes, we could use those to start to identify other existing accounts that have similar attributes and similar properties and similar risk. And you can do this today. We don't necessarily need a huge data science project to do this. I mean, to do serious prediction is going to be a lot of work. But you can do this today, even without needing a huge data science project. What I would say is if you start with existing, if you audit S3 access, look for cases where credentials are embedded in code blobs. Even code blobs that don't end up in public repos, because if a code blob or if a credential is in a script or a code snippet that ends up on an instance that somebody ends up getting execution and persistence and landing on, then it's still going to be exposed. So credentials in code. And then the next thing I would say is take an inventory of all of your IAM accounts that have S3 access, and especially the ones that have S3 access but they have not used it. Because sometimes there are accounts out there that are overprivileged and they have access they don't need. And so identify everything that has S3 access but's not using it, and wherever possible, remove that access so that S3 access is reduced to the workers and things that really need it. And then next, look for S3 access. Look for roles and accounts that have significant S3 access that are running in your attack surface, like in your internet-facing web services, or things that are 1 degree of separation from your internet-facing attack service, like middleware, database layer, anything running on an instance that's exposed to external attack. And sometimes those workers will need to have S3. Sometimes you can't necessarily change that, but if you can move the S3 deeper into the attack surface layers so that there are more degrees of separation and reduced exposure to internet inbound attack paths, that's potentially another benefit as well. If we do that, that would have been effective in several of the cases that we've seen so far. And so, the good thing about that is there's no disruption, right? Because we're not aggressively blocking anything. We're identifying risk and then getting to a point where we have sufficient consensus to go and actually do something about that risk in terms of modifying access. But this is risk that hasn't been realized yet, so we don't need to act urgently. We can do it in a thoughtful and deliberate way. So, in terms of takeaways, what I would say is within the first 90 days, see what you have in terms of cloud accounts and cloud logging. And if you have cloud trail data or the Azure equivalent, within the next, say, 6 months, within the next 90 days to 6 months, think about what your incident response strategy for Exfil needs to be. Does it need to be fast and aggressive, or does it need to be more slower and cautious? Because every organization is different. And then work on getting some anomaly detection running within 6 months, either in your existing SIEM or possibly in a data science tool. So that is my talk. I'm not able to put the name of the location of the repo where these notebooks exist on screen right here. But if you want to take that stuff home and play with it, just hit me up and I'll tell you I can give you the location of the repo.